What is going on, wonderful people? It's Medicosis Perfectionalis, where medicine makes perfect sense. Welcome back to my playlist called Fluids, Electrolytes, and Acid-Base Disturbances. In previous videos, we talked about the electrolytes in detail. We talked about sodium, potassium, magnesium, phosphorus, calcium, and even chloride. We talked about isotonic, hypotonic, and hypertonic fluid disorders. Today, we shall start talking about acids and bases. Today, I will show you not one, not two, but 3 methods to tackle any acid-base problem. First, do not confuse acidosis with acidemia. Acidemia means I have tons of acids in my blood. Acidosis is a condition that produces acids. So acidosis is a term in pathology. Acidemia is a laboratory term. Similarly, alkalemia means my blood has lots of bases. Alkalosis means I have a condition that produces bases, or a condition that eliminates acids. Click the like button, click the subscribe button, and let's get started. Before we get started, you need to be familiar with my rule of 4s. Everything that you need to know is 4. Sodium. What's the normal serum sodium in the blood? The normal serum sodium concentration in the plasma is 140 milliequivalents per liter. How about chloride? 104 instead of 140. Of course, you know that sodium is a cation, but chloride is an anion. Next, today's topic, acids and bases and arterial blood gases. What's the normal arterial partial pressure of carbon dioxide? It is 40, the rule of 4 again. How about the normal bicarbonate concentration in the blood? 24. How about the pH? 7.4. The pH does not have a measuring unit. The normal potassium concentration in the plasma is 4 milliequivalents per liter. Phosphate, 4. Albumin, 4. However, phosphorus is milligrams per deciliter, but albumin is grams per deciliter. TSH is 4. And because the concentration of hormones is so tiny, we measure them in microns, or in micro unit per ml. You need to know the range. Yes, carbon dioxide is 40, but it ranges between 35 and 45. How about bicarbonate? Yes, it's 24, but there is a range. 22 to 28 is normal and acceptable. pH is 7.4. Yes, the range is 7.35 to 7.45. 7.4 is the average, 24 is the average, and 40 is the average. Do not confuse the hydrogen ion concentration with the pH. The beauty of the pH as a concept is that it took a number that is extremely tiny and made it make sense, made it big enough so that it's easy to deal with. So, if the concentration of hydrogen ions in my blood is 1 times 10 power negative 7, the pH of my blood is just 7, which is neutral. This is the neutral pH, which means it's neither acidic nor basic. Or you can say that it has an equal concentration of acids and bases. pH of 7 is neutral. But is this the normal pH of the blood? No, the normal pH of your blood is 7.4, slightly basic, slightly alkaline. Why is this? Because you have an alkaline reserve known as bicarbonate. Why do I have an alkaline reserve and not an acidic reserve? Because your natural, normal, everyday metabolism secretes acids and not bases. And because you secrete tons of acids every day, you need to counteract them and buffer them by means of a base. So you have a basic alkaline reserve, not an acidic reserve, and this is a very basic fact. For the chemistry buffs out here, what is the measuring unit for hydrogen ion concentration? If you remember your chemistry, the measuring unit was molar, and 1 molar equals what? Equals 1 mole per liter. But what's the measuring unit of pH? It does not have a measuring unit. And because I took the negative log of the hydrogen ion concentration to form the pH, therefore, if my blood is super acidic, meaning it has tons of hydrogen ions in it, the pH will be low. Conversely, if I do not have enough hydrogen ions, hydrogen ion concentration is low, which makes the pH high. So we can say with confidence that thanks to this negative log of something, now the relation between the hydrogen ion concentration and the pH is inverse. When this goes up, this goes down. When this goes down, this goes up. So if I have acidemia, too much acids, the pH of my blood will be low. But if I have alkalemia, less acids, my pH will be high. You see this equation right here? I call it the golden equation. Let's focus on this part. Here you have carbon dioxide. Where did you get that from? Let's say from metabolism, because remember, the cell requires arterial blood supply, and the artery brings what? Nutrients and oxygen to the cell to use that in cellular respiration, #metabolism. And then when the cell is done, it's going to dump its carbon dioxide onto the venous side. This is the carbon dioxide that I'm talking about. And of course, you know that you have water everywhere in your body because your body is about 2/3 water. So eventually the carbon dioxide is going to hit a water molecule. And when this happens, you know what's going to happen? Well, you're going to make this H2CO3. It has 2 hydrogens, it has 1 carbon, and it has 3 oxygens. What is the name of this doofus? It's called carbonic acid. Carbonic acid. Do you think carbonic acid is an acid or a base? After deep thinking and contemplation, of course it's an acid. It's called carbonic acid, for heaven's sake. And therefore, every time you think of carbon dioxide, you should think of an acid. So what if my body is retaining tons of carbon dioxide? What's going to happen? I will have acidosis. What if my body is eliminating carbon dioxide very quickly, like it's nobody's business? I will have alkalosis. Because when you get rid of the acid, you become alkalotic. And when you become alkalotic, the pH should rise, all things else being equal. So acidosis, low pH. Alkalosis, high pH. In this lovely equation that I call the golden equation, we see that carbon dioxide is here and bicarbonate is on the opposite side. To get rid of carbon dioxide is the lungs' function. To eliminate bicarb is the kidney's function. It does not have to be eliminate, I should say regulate. The lung regulates your carbon dioxide and a healthy kidney regulates your bicarbonate. This is what keeps you in balance. Next, some facts to keep in mind. Suppose that I eat a lot. I ate a lot today. So what's going to happen? Lots of metabolic production. Therefore, carbon dioxide is going to rise. There is no question about it. Next, let's talk about ventilation. Let's say that I started breathing fast and fast and fast. Breathing fast causes what? Well, this is in the denominator and this is upstairs. So therefore, if I breathe fast, my carbon dioxide will decrease. So increased respiratory rate or tachypnea is accompanied by decreased carbon dioxide. So we can say that conversely, if I decrease my respiratory rate, bradypnea, what's going to happen to carbon dioxide? It will build up. So tachypnea eliminates the acid, causing alkalosis. But bradypnea builds up the acid, causing acidosis. And since increase or decrease respiratory rate is the lungs' fault, we're going to call this respiratory alkalosis and respiratory acidosis, respectively. So hyperventilation causes respiratory alkalosis, whereas hypoventilation causes respiratory acidosis. So the ventilation rate or the alveolar ventilation is directly correlated with carbon dioxide elimination, and that's why it's inversely correlated with the carbon dioxide that's left in the blood that was not eliminated. So increased alveolar ventilation will increase carbon dioxide elimination, leaving less carbon dioxide in me. Less acid equals respiratory alkalosis. Conversely, if I have hypoventilation, carbon dioxide elimination will decrease, leaving tons of carbon dioxide within me, causing respiratory acidosis because carbon dioxide is an acid. When the acid accumulates in my body, we call it acidosis. So between alveolar ventilation and carbon dioxide elimination, we have a direct correlation. But between alveolar ventilation and the carbon dioxide pressure in the artery, in the body, it's an inverse correlation. That's why you can lump this one with this one and form a hypothetical equation like this. If you wish to download these doozy colorful notes, go to medicosisperfectionalis.com. I help you learn, understand, and pass exams. If you want me to personally tutor you, reach out to me on my website. Every day and in every way, I'm getting better and better. Every day and in every way, I am getting acidic and more acidic. Why? Because you make lots of carbon dioxide and your metabolism secretes lactic acid, sulfuric acid, phosphoric acid, uric acid, etc. Who's gonna get rid of this volatile acid? The lungs, because the lung is airy. It takes care of the volatile stuff. However, the heavy stuff cannot be handled with the lungs because the lungs can't handle the truth. Who can then? Kidneys can. The kidneys will get rid of the fixed acids like lactic acid. This is one of the most important equation ever. Please pause the video right now and write this equation gazillion times. pH is proportional to bicarbonate on the numerator, this is the kidney's job, divided by carbon dioxide in the denominator, and this is the lungs' job. To understand the profundity of such an equation, we're going to imagine a patient who has kidney failure. Imagine that the kidney is toast. You know what's going to happen to my bicarbonate? It will be wasted. It will be consumed. And when the numerator decreases, what's going to happen to the pH? Decreases. When the pH goes down, would you call this acidosis or alkalosis? We're going to call this acidosis or acidemia. Who is at fault? The kidney. So we call it metabolic acidosis. Got it. Conversely, let's suppose that I have a problem. For some reason, my bicarbonate keeps going up. What's going to happen to the pH? It will keep going up. What would you call this? Metabolic alkalosis. Next, let's tamper with carbon dioxide. Suppose that my lung is hyperventilating. If you're hyperventilating, your carbon dioxide decreases. When your carbon dioxide decreases, the acid is decreasing, so you're becoming more alkalotic. What would you call this? Since it's the lung's fault, we're going to call it respiratory. Since the pH is going up, it's respiratory alkalosis. Let's do the opposite. Suppose that my lung, for some reason, is hypoventilating. If you are hypoventilating, the carbon dioxide will pile up in the body, and when the denominator goes up, this value will go down, so the pH decreases, and we call this acidosis due to a lung problem, so we call it respiratory acidosis. And that's why this equation is of utmost importance. So we have acidosis, we have alkalosis. The acidosis could be metabolic, blame the kidney or a metabolic process, or it could be respiratory, blame the lungs. How about alkalosis? It could be metabolic, blame a metabolic disorder, or respiratory, blame the lungs. Next, if the primary disorder, if the primary condition, if the original disease, if who at fault is the lungs, i.e. it's a respiratory problem, whether it's respiratory acidosis or alkalosis, then the lung is the problem. The lung cannot correct the problem because the lung caused the problem. Who's gonna compensate then? Who's gonna help and correct then? The kidney has to do the heavy lifting. But what if the primary disorder is the kidney? What if the kidney messed up first? Then the lung has to correct that. So, a primary respiratory disorder is corrected or compensated by the kidney. But if it's a kidney disorder, it will be compensated by the lungs. Since the normal pH is 7.4 or the range is 7.35 until 7.45, therefore, if the pH is low, less than 7.35, we call it acidemia. If the pH is high, we call it alkalemia. Here's the first method to solve any acid-base problem. I've told you that I'm going to teach you 3 methods. Here is number 1. First, you look at the pH. All right, if the pH is low, it's acidosis. If the pH is high, it's alkalosis. But what kind of acidosis? Is it respiratory or metabolic? Or what kind of alkalosis? Is it respiratory or metabolic? How should I know? You look at the pH and one other thing. You could look at the pH with the bicarb or the pH and the CO2. But do not compare the bicarb to the CO2. Otherwise, this method is not going to work. So I prefer to look at the pH and the bicarb. And then what? If both of them are moving in the same direction, for example, pH is decreasing and bicarbonate is decreasing, or pH is increasing and bicarb is increasing, we call this metabolic disorder. So it's going to be metabolic acidosis or metabolic alkalosis. However, if you looked at the pH and the bicarb, but they were moving in the opposite direction. One is up, the other is down. Or one is down, the other is up. Then it's respiratory. So here's the mnemonic. If they're moving in the same direction, it's a metabolic disorder. But if they are moving in the reverse direction, therefore it's a respiratory primary disorder. Example, the pH was low, okay? So we call this acidosis. But what type of acidosis? You're gonna look at the pH and something else. Let's look at the pH and the bicarb. The pH is decreasing, the bicarb is decreasing. Voila, metabolic acidosis because they are moving in the same direction. Same has ME and metabolic has ME. But what if it's an acidosis, but I looked at the bicarb was up. Now the pH is low, but bicarbonate is high. They are moving in the reverse direction. And if it's the reverse direction, it is respiratory acidosis. Why respiratory? They're moving in the reverse direction. Why acidosis? Because the pH is decreasing. Conversely, I looked at the pH, it was high. I'm going to say alkalosis. But what type of alkalosis? You're going to look at the pH and something else, like the bicarbonate. pH is high, bicarbonate is high, so it's alkalosis, and they are in the same direction, so it's a metabolic alkalosis. Okay, another case, the pH was high, however, bicarbonate is low. pH is high, it's alkalosis. They are moving in the opposite direction or in the reverse direction, it is respiratory alkalosis. Method number 2 to solve any acid-base problem is to use this equation. I call it the golden rule of acid-base. What's that? As in, do unto others what you want them do unto you. Here we're gonna say, do unto the lungs what you want the kidneys do unto you. Let me explain. Let's take this example. A patient's pH is low, bicarbonate is low, and carbon dioxide is low. Where should I start? You should start with the pH low, okay? The pH here is low. So what do I call this? If the pH is low, we're going to call this acidosis. That's easy. And then what should I do? Ask yourself this. What are the possibilities that can lead to a low pH? Well, it's either a decrease in the numerator or an increase in the denominator. These are the two only ways on God's green earth. If it's the bicarbonate that caused the decrease in pH, we're going to call this what? Metabolic acidosis. But if it's the lung that raised the carbon dioxide causing the acidosis, we're going to call this respiratory acidosis. Now, which of these actually happened? You look at the patient's actual lab results. The bicarb is low. The carbon dioxide is not high. Oh, so now I know that it's the kidney's fault. So, the first thing that happened is that bicarbonate went down. And next thing that happens is that the pH went down. They are moving in the same direction. It is metabolic. When the kidney is at fault, we're going to call this metabolic. When the numerator is the problem, it's metabolic. So this is metabolic acidosis, okay? So far, so good. But why did the patient's carbon dioxide decrease like this? Because you have to do unto others what you want them do unto you. Do to the denominator what the numerator did to you. What happened to the numerator? It went down. So therefore, the body will try to bring carbon dioxide down. Why? Because when you have a numerator decreasing and a denominator decreasing, you know what's going to happen to the pH? It will normalize. It will become normal. Do unto others what you want them do unto you. So therefore, what's the diagnosis here? The kidney is at fault. It's a metabolic fault. So it's a metabolic acidosis. Okay? I got that. Now, why did the carbon dioxide decrease? Because the lung is trying to compensate. So we call this partially compensated metabolic acidosis. Why do you say partially compensated and not fully compensated? Because if this were fully compensated, you will see a normal pH, which is not the case. The patient's pH is actually low, not normal. So it's partially compensated. The lung is trying to correct the metabolic disorder, but the lung is not there yet. It's moving in the right direction. If you want to see more videos like this in the future, please drop a test tube emoji in the comments. What do you call a test tube that has finished its education? A graduated cylinder. Enough with the dad jokes. So the first method is the mnemonic. If they are moving in the same direction, it's metabolic. But if they are moving in the opposite direction, reverse, it's respiratory. Methodology number 2 is the numerator and the denominator. Do unto others what you want them do unto you. Method number 3 is the tic-tac-toe for acid-base disturbances. And to illustrate this, let's deal with real examples. Before we do this, remember that the carbon dioxide is normally 40, but it ranges between 35 and 45 millimeters of mercury. As for bicarbonate, 22 to 28, and the pH is 7.4, which is 7.35 to 7.45. Let's start with example number 1. With each one of these, I want you to pause the video and try to solve the problem yourself. What is going on here? Is it metabolic acidosis, metabolic alkalosis, respiratory acidosis, or respiratory alkalosis? And is it compensated or not compensated? And if it's compensated, Is it fully compensated or partially compensated? Now pause. First method, look at the pH alone. Okay, the pH is low. Why? Because the normal pH is from 7.35 to 7.45. Therefore, 7.16 is low. And when the pH is low, what do you call this? I call this acidosis. Next step, take the pH and something else. I'm going to look at the pH and bicarb. Okay, the pH has decreased. All right, and what happened to bicarb? I know that the normal bicarb is from 22 to 28 milliequivalents per liter. 11 is low. So the bicarb also decreased. When they are moving in the same direction, it is metabolic. So this is a metabolic acidosis. This method told us that it's metabolic acidosis, which is correct. However, it cannot tell us whether it's compensated or not. Which means I'm going to use the second method now. The second method was this famous equation. pH is directly related to bicarbonate, which is the kidney's responsibility, divided by the PCO2, which is the lungs' responsibility. And then what? This pH is low. Okay, what caused that? Well, if the bicarb decreases, oh, that makes sense. Low bicarb causes low pH. So this is the first thing that happened, which is decreased bicarb, and this is the second thing that happened. All right, let's write that down. Since the pH is low, it's acidosis, and since bicarbonate is low, we're gonna call it metabolic acidosis. Because if the problem started in the numerator, it's a metabolic issue. This is metabolic acidosis, okay? Now, is it compensated or not? Let's look at the carbon dioxide. What's the normal carbon dioxide? From 35 to 45. So is this carbon dioxide normal? Yes, it is normal. Therefore, the lungs did not do anything to try to compensate. Normally, ideally, the lung should bring that carbon dioxide down because you should do unto others what you want them to do unto you. If the numerator went down, I need to bring the denominator down. But the lungs did not do this because the carbon dioxide remained the same. Therefore, this is unambiguously uncompensated metabolic acidosis, and this is the final answer. Same question, method number 3 is the tic-tac-toe. The pH is low. A low pH is something acidic, so you put the pH under the acid column. Next, you look at the bicarb. The bicarb is 11. Bicarb itself is a base. When the base is low, it's an acidic thing. So I'm gonna put bicarbonate under the acid. When you see two things together like this, when you see the pH in the same column as the bicarb, it means that the bicarb is the cause of this pH disturbance. So the bicarb is metabolic. This is metabolic acidosis. So this is what we know so far. The patient has metabolic acidosis. Next, is it compensated or not? Let's look at the carbon dioxide. Carbon dioxide is 35. Normally is 35 to 45. So this carbon dioxide is normal. Normal means neutral. So I'm going to put carbon dioxide here. Now, if the lung was actually compensating, then the carbon dioxide should be pushed to the opposite side as the pH. Ideally, you should push the carbon dioxide here in order to pull to the right to counteract the pH's pull to the left. However, this is the la-la land that did not happen. The lung did not do anything to the carbon dioxide, leaving it right smack in the middle, which means this is uncompensated metabolic acidosis, and now I've showed you the 3 methods. All of that was question number 1. Question number 2 is upon us now. Here are the numbers. Please pause and try to use the 3 methods to come up with the answer. First, write down the normals. pH is 7.35 until 7.45. Bicarb is 22 to 28. That's normal. The normal carbon dioxide is 35 to 45. Next, look at the pH. What happened to it? This pH is high. Then, look at the pH and something else. I'm going to look at the bicarb. This bicarb is low. Bicarb is low, but pH is high. They are moving in the opposite or the reverse direction. So this has to be a primary respiratory disorder. Is it respiratory acidosis or alkalosis? Easy. Look at the pH. The pH is high. This is respiratory alkalosis. Is it respiratory alkalosis that is compensated or uncompensated? This method cannot tell us. So therefore, I need my golden equation, which says pH equals bicarb on top, this is the kidney's responsibility, divided by carbon dioxide at the bottom, and this is the lungs' responsibility. Okay, what happened? Well, the pH is high, all right? For the pH to be high, it's either because of high bicarb, which did not happen, or low carbon dioxide. Yes, this carbon dioxide is low. So the low carbon dioxide happened first, causing the pH to go up. When the pH is up, it's alkalosis. When the carbon dioxide is the problem, it's called respiratory alkalosis. Next, did the kidney try to correct this and compensate? Look at what happened to bicarb. Yes, the kidney tried to compensate because you want to do unto others what you want them do unto you. If the denominator decreases, you better lower the numerator as well. So yes, we lowered, so cancel, and the pH will normalize. Yes, this indeed is compensated respiratory alkalosis. The question is it fully compensated or partially compensated? Look at the pH. Is this pH normal? Not yet. Therefore, this is partially compensated respiratory alkalosis. But what if I looked at the pH and it was within normal limits? We will call it fully compensated respiratory alkalosis. Here is the same problem, but we're going to use the tic-tac-toe. This pH is high. When the pH is high, it's a basic thing. It's an alkaline thing, so the pH goes to the right column. Look at the bicarb. This bicarb is low. Bicarb is a base and the base is low. A low base is an acidotic thing. Okay, let's look at the carbon dioxide. This carbon dioxide is low. Carbon dioxide is an acid. When the acid is low, it's a basic thing. Now look at this. Who followed the pH to the same column? Carbon dioxide did. So therefore, who is responsible for the fact that the pH is basic? Carbon dioxide is. If carbon dioxide is responsible, this is a respiratory alkalosis. Is it compensated or not? Well, the bicarb started here, but the kidney is doing a great job by pushing the bicarb this way to counteract the pH which went the other way. Yes, this is being compensated, so I'm going to call this compensated respiratory alkalosis. Is it partially compensated or fully? Look at the pH. Is it neutral? No, the pH is high. The pH is basic. So we're not there yet. It's partially compensated respiratory alkalosis. As the kidney keeps pushing and pushing and pushing the bicarb to the acidic side, i.e., as the kidney keeps lowering the bicarb, this pH will eventually go from basic to neutral. When it does that, we're going to call it fully compensated respiratory alkalosis, but we're not there yet. Next, question number 3. Please pause. First, you look at the pH alone, okay? Normally, the pH should be between 7.35 and 7.45. This is within the range, so this is normal, okay? How about this? It's within the range and is normal. How about this? It's within the range and is normal, so therefore this is a normal person. This is not a patient. Same question using the golden equation. Do unto others what you want them do unto you. The pH is normal, the bicarb is normal, and the carbon dioxide is normal. Everyone is happy. This is a normal case. Using the tic-tac-toe, the pH is normal. It goes under neutral. The bicarb is normal. It goes under neutral. The carbon dioxide is normal. It goes under neutral, and this is a normal person. Question number 4, let's go. Please pause. Normal pH is 7.35 to 7.45, so this pH is high. Okay, let's look at the bicarb. Bicarb should be between 22 and 28. This bicarb is normal. Let's look at the carbon dioxide. It should be between 35 and 45. This carbon dioxide is low. So when the pH is high, what do you call this? I'm going to call it an alkalosis. Then you look at the pH and something else. This something else is the carbon dioxide. One is high, the other is low. When they are in reverse, it is respiratory alkalosis. Is it compensated or not? This method cannot tell us, which means I need my other equation. I need the golden equation, which states that pH is proportional to what's happening to the bicarb, which is a kidney matter, divided by what's happening to the carbon dioxide, which is a lung matter. All right, the pH increased, okay? So what's the cause? It could be bicarb went up or carbon dioxide went down. Bicarb did not go up, but carbon dioxide did go down, which means this is the primary disorder which raised the pH, okay? So the primary disorder is respiratory. I'm going to call it respiratory, which caused high pH, which is alkalosis, respiratory alkalosis. Did the kidney do anything to try to compensate? No, the bicarb did not budge an inch. Therefore, bicarb did not move. The kidney is not trying to compensate, which makes this uncompensated respiratory alkalosis. Same question using tic-tac-toe. This pH is high. High pH is a basic thing. We're going to put it here. This bicarb is normal, which means neutral. Bicarb goes here. And this carbon dioxide is low. The acid is low. Low acid is a basic condition. So therefore, who caused the high pH? The lungs did. Therefore, we're going to call this respiratory alkalosis. Respiratory because the carbon dioxide shares the same column as the pH. And alkalosis because the pH is high. Is it compensated or not? Well, look at the bicarb. Is the kidney trying to push bicarb to the opposite side as pH? The answer is no. The kidney did not do this. So this is uncompensated respiratory alkalosis. Next, here's question number 5. Please pause. Let me know your answer in the comments. And here is question number 6. Please let me know your answer in the comments. Let's see who is going to answer it first. You will find the answer key in the following video in this fluids, electrolytes, and acid-base playlist. Notice, in today's lecture, we talked about just a primary disorder. It was either primary metabolic acidosis or metabolic alkalosis or respiratory acidosis or respiratory alkalosis. But what if the patient has many things happening together? For example, you can have a patient with high anion gap metabolic acidosis while simultaneously having normal anion gap metabolic acidosis while simultaneously having respiratory alkalosis. What? Acidosis and alkalosis together? Yes. And all of these are primary disorders, not compensations. Can this happen in real life? It happens all the time. If you want to know how can you solve these complicated, combined, mixed acid-base disorders, I have a special course on this. It's called the Acid-Base Imbalance course, which comes with videos, notes, and cases. You can download it today at medicosisperfectionalis.com. It will teach you about the serum anion gap, the serum osmolar gap, the urine anion gap, and the stool osmolar gap. It will also teach you about base excess and base deficit. To take it to the next level and learn about cardiac arrhythmias, strokes, myocardial infarction, ARDS, acute limb ischemia, drowning, and many toxidromes and their antidotes, download my emergency medicine high yields course at medicosisperfectionalis.com. It comes with videos, notes, and cases as well. There are more than 600 premium videos available on this channel when you click the join button and choose the highest tier. Please subscribe, hit the bell, smash like, support my channel on Patreon, PayPal, or Venmo. Go to my website to download my courses, notes, and cases, or if you would like me to personally tutor you. Be safe, stay happy, study hard. This is Medicosis Perfectionalis, where medicine, chemistry, and physics make perfect sense.